We're going to look at another type of metathesis reaction, the reaction between acids and bases. So let's look in more detail at acids. And here we have a bottle of concentrated hydrochloric acid. This right here is some sodium carbonate, and we add the two together, we get a bubbly mixed reaction. And this also happens when you take sodium carbonate, which is a major component of baking powder or baking soda, and you add vinegar to it, which is an acid. You'll get these bubbles, and we'll see very shortly how to write the chemical equation for this. Acids have several different definitions, and we're going to look at the two common ones found in freshman chemistry. The Arrhenius definition of an acid is a substance that increases the concentration of H+ when it is dissolved in water. And the Bronsted-Lowry definition defines acids as a proton donor. Well, let's look at this definition of proton. We know that protons are subatomic particle in the nucleus. So what does that have to do with chemistry? Well, let's look at H+. If we look at H on the periodic table, we see that it has one proton, it has one electron, and most hydrogens have no neutrons. Neutrons are generally used to hold protons together. So if all we have is one proton, we don't need any neutrons. So if we look at H+, we have a hydrogen atom that has lost its electron. So it has no neutron, no electron, so really it's a proton. So when we use the word proton in acid-base chemistry, this is the symbol we use for it. Now, as I pointed out earlier, there are 7 strong acids. All of the other acids are weak. You must know the names and formulas of these, and if you can't memorize them, you'll definitely want to write it on your card. Okay, now let's look at how strong acids act as strong electrolytes. Hydrochloric acid, just by itself, not dissolved in water, is actually a gas. It's a covalent compound, but because it's an acid, when it is dissolved in water, it dissociates into H+, Aq, the proton, and the chloride ion. So even though this is a covalent compound by definition, it's made up only of nonmetals, it is an acid in water. It happens to dissociate into this H+ and chloride anion. All acids that we're going to talk about will dissociate into the H+, and then whatever's left will be the other ion. So if we look at nitric acid, it's going to dissociate into the proton and the nitrate ion. And these will be Aq, completely surrounded by water, completely dissociated. And sulfuric acid is what's known as a diprotic acid. And to keep things simple, we're just going to say it completely dissociates. Even though that's not completely true, for our purposes, it works. Both nitric acid and sulfuric acid are liquids in their absolutely pure state, but we're going to care about them as dissolved in water only. And when these are dissolved in water, none of the covalently bonded compounds exist. They exist completely as the ions, which is what makes them strong electrolytes. Bases are kind of the opposite of acids. The Arrhenius definition of an acid is a substance that increases the concentration of hydroxide when dissolved in water. A broader definition is that of the Bronsted-Lowry, which defines them through their chemical reactivity. The Bronsted-Lowry definition of a base is any substance that accepts a proton in a chemical reaction. Now, the 7 strong bases that you must know are the soluble metal salts or soluble metal ionic compounds of the hydroxide ion and the alkali metals, the first column of the periodic table, and calcium, strontium, and barium, the heavier alkaline earth metals. Now, here is how an acid-base reaction works anything that has a hydrogen could potentially act as an acid, and anything that can accept that proton could potentially act as a base. This slide goes a little bit beyond what we're going to be dealing with in this class. In 152, we'll look at these processes in detail. But here we see the only weak base that you're going to be responsible for, ammonia. Now let's look at what happens when bases dissociate. Now, bases are a little easier than acids because bases are ionic compounds. And let's look at an alkali hydroxide, lithium hydroxide. When it is dissolved in water, we get the lithium ion and we get the hydroxide ion. And the hydroxide is what makes this a basic substance. And then the calcium hydroxide, let's look at an alkaline earth base. The alkaline earths all have a positive 2 charge, so they have 2 hydroxides for each cation. So when the alkaline earth bases dissociate, we're going to get 1 cation, in this case the calcium, and 2 hydroxides. And as is in the case of the, that's right, H2O here, as is in the case of the acids, none of these remain together when they're dissolved. The lithium does not stay with the hydroxide. Each lithium cation is completely surrounded by water, each hydroxide completely surrounded by water, each calcium surrounded by water, and each hydroxide completely surrounded by water. And this is why these are strong electrolytes, completely breaking apart into their ions. Now let's look at acid-base reactions. Acid-base reactions are a type of metathesis or double replacement or exchange reactions, and they are often called neutralization reactions. And this is because their pH goes to neutral usually when they react. Now here we have an acid and a base. Now this is the one type of acid where the hydrogen may not come in the beginning. This is an organic acid known as acetic acid. It's very common. It's the acid that's found in vinegar, and it's very inexpensive, so it's used a lot in freshman chemistry experiments, so we see it a lot. But organic chemistry doesn't follow the rules of inorganic chemistry. And this Cu right here gives us a clue as to its structure. So a lot of times when you see acetic acid, it will be written in this way, CH3 Cu. It is the last hydrogen, or if it's written the other way, the first hydrogen, that is the acidic hydrogen, the hydrogen that is going to react with the hydroxide. Now the crux of our acid-base reactions are going to be the incredible affinity that a proton and hydroxide have for one another. As soon as these two species see each other, they form a molecule of water. And when water is formed in water, it's not AQ, because water can't be dissolved by water. If water is surrounded by water molecules, then it's in the liquid state. So anytime a proton sees a hydroxide, we always form a water molecule. So here is our acidic proton at the end of our acetic acid. It reacts with our hydroxide to form water. We are left with sodium that has a positive charge and our acetate ion, which has a negative charge. So we form a compound. Now, here we have our cation at the end. Again, this is very atypical. This is something that only organic chemists do. And in your mastering chemistry and on your tests that I give you in class, the cation is always going to come first. Now let's take a look at a strong acid reacting with a strong base, hydrochloric acid and sodium hydroxide. As soon as this proton sees a hydroxide, it's going to form water. Water will always be a product between a strong acid and a strong base. What's left is my sodium with a positive charge, my chloride with a negative charge, and I form sodium chloride. So when a strong acid reacts with a strong base, we're going to get a salt and water. Let's look at the ionic equation. I dissociate my hydrochloric acid into the proton and chloride AQ, aqueous, and my sodium hydroxide into the sodium and hydroxide, AQ. And remember to pay attention to the charges. Then on the product side, my sodium and chloride are still going to be AQ because that sodium chloride is a soluble ionic compound, which is a strong electrolyte, but water is a molecular compound, so it does not dissociate. So to get my net ionic equation, I cross out my spectators, sodium and chloride, they're the same on both sides, and I'm left with H plus the proton, AQ, plus hydroxide, AQ, giving me water as a liquid. And this is always going to be the net ionic equation for the reaction between a strong acid and a strong base.